All right, so we're going to do 4.2 today, which is the natural exponential function. And our learning objectives for today are we're going to evaluate the natural exponential function. We're going to graph the natural exponential function. And we're going to calculate continuous interest. Okay, so first we're going to just kind of investigate a little bit about the number e. See if you can find e in your calculator somewhere. So once you click on E in your calculator, you're going to see, if you just hit enter, that it's going to be approximately 2.718281825.9-ish, okay? And it keeps going without any pattern. It's an irrational number. Okay, so we know that E is between 2 and 3. But I want to investigate a little bit. If I just started plugging in some values for n here, it got bigger and bigger. So let's put 1 right here, and let's see what happens when I plug this in. So 1 divided by 1 is 1, plus 1 is 2, and 2 to the first is 2. So do that with some more values. See what happens if you plug in 5. And then let's jump to 10. Try 100. 1,000, and try 1,000,000. All right, so when you plug those into your calculator, you can pause me while you're doing that. This is what I get out. What do you notice is happening? This value is getting closer and closer to E. So I can see here, as n goes to infinity, this equation is going to go to E. And then right here, which one is E? Rational or irrational? Kind of said that. I almost forgot to fill it in. It is irrational, and why? Because its decimal is non-repeating and non-terminating. Okay, well, let's graph some of these values for E. And you can get your graphing calculator if you want. Or we said, well, I know that E is between 2 and 3. So I know this function has to be between 2 to the x and 3 to the x. So I'm going to sketch those on really quick. So smartboard is not aligned really well. So at 0, I'm at 1. Actually, give me a second. I'm just going to align this really quick. Make my life easier. I hope that didn't stop it. All right, sorry about that. Let's keep going. So let's do 2 to the x first. So at 0, I'm at 1. At 1, I'd be at 2. At 2, I am at 4. And I know I have a horizontal asymptote. At y equals 0. Okay, well, what about 3 to the x? Again, at 0, I'm at 1. At 1, I'm at 3. At 3, I'm at 9. And looks something like that. So if I wanted to go e to the x, I know that I'm going to be between these two graphs. So e to the 0 is still 1. E to the first is e, which we said is about 2.7-ish, so it's in between there. So it's going to grow in between those two. So it's kind of squeezed in. This didn't ask for it, but let's go ahead and state the domain, range, and the asymptotes. So my domain is going to be all real numbers. The range, it's all the way down to 0, but not hitting 0, so it's open, and that goes up to infinity. And your asymptote, you only have a horizontal asymptote going on, and that was at y equals 0. Okay, so let's do this next one. First, let's try to do it with some transformations, and then we can check with our graphing calculator. So what's happening here? What does this negative do versus this negative? So this negative out in front is going to reflect over the x-axis, and this negative inside makes it the odd. It's going to reflect over the y-axis. So first thing I'm going to do is go ahead and get e back up there. So at 0, I'm at 1. At 1, I'm at 2.7-ish. Looks something like this. That horizontal asymptote at 0. And then I'm going to take this point right there, and I'm going to reflect it over the x-axis and over the y-axis. So when I reflect over the x, it comes down here, and the y, it just stays because it's right on the y-axis. So let's do this next one. I'm going to take this point, reflect it over the x-axis, and then reflect it over the y-axis. So I get something like that. Oops. Just lost. Okay. So filling in, I can see that I still have my horizontal asymptote. But now it's just basically reflected over the x and y axis. This would mean that if I do that line y equals 1 and folded them together, they're going to meet. The domain here is from negative infinity to infinity. Your range is from negative infinity until 0, but doesn't touch 0, so it's open. And your horizontal asymptote is y equals 0. So you can definitely check this in your graphing calculator to see how you do. Make a table of values. See what happens when you plug in 0. I bet you get -1. And you can continue to do that with, let's say, -1. You're going to get out negative e, basically. And check those to see how you do. Okay, let's do some more transformations. You guys are pretty good at this one. X on the inside here and 4 on the outside here. So this one on the inside is always the opposite, don't forget. So I'm actually going to go right 3, and that +4 at the end is going to send me up 4. We don't do the opposite of the end, just on the inside. So I'm going to start with my graph of e to the x. 0, 1, 1, I get out e, horizontal asymptote, and I'm going to go take this point and go right 3. So 1, 2, 3, and up 4. 1, 2, 3, 4. So I'm going to plot it right there. I'm going to take this point, go right 3. 1, 2, 3, and up 4. 1, 2, 3, 4. And what do you notice about what should the horizontal asymptote do? If everything is getting shifted up, like so you're pushing it up 4, this asymptote that was at 0 is now also going to get shifted up to 4. So as you go and make your chart or your graph here, you're going to get it with the asymptote now at 4 instead of at 0. And if you'd like to put that in your calculator and make a table and check some of those values, that'd be great. Okay, continuously compounded interest. So we have talked about this compounded interest before, this formula right here. And we're going to see if we can manipulate it to get us something that goes continuously. So basically, its n is going to infinity here. It's constantly being compounded. So as I do that, I'm just going to first rewrite and make this n over t to the RT. So once I get this guy going, I see what we learned on that first section is n goes to infinity. This is just going to go to e. So basically I'm left with p, that whole thing in the middle goes to e to the RT. So let's use that formula. All right, doctors use radioactive iodine as a tracer in diagnosing certain thyroid gland disorders. This type of iodine decays in such a way that the mass remaining after T days is given by the formula below. M of T is measured in grams. So I'm just going to kind of write what they gave me first. They said T is going to be in days, and M of T is in grams. All right, so A says find the mass at the initial time. Well, we can plug in 0, that's the initial time when time is 0. So that gives me e to the 0, which is 1, and 6 times 1 is 6. Or you can just know from your formula, this guy right here was your P, which is your initial amount that you started with. So at time 0, you should get out 6. That's how much you started with. Okay, part B, how much is left after 20 days? And this one I'm definitely going to put into my calculator. Make sure when you do this that you put this whole, 0, this whole thing all in the exponent, okay? Or you're not going to get the right answer. So this is about 1.0531, and it's measured in grams. I think I forgot to write that up here too. There we go. Okay, one more thing that we're going to discuss, and that's logistic growth. So in exponential growth, things just keep going and going and going up forever and ever and ever. So think about that if it's possible. I know you like think of rabbits in Algebra 1, like they keep multiplying and multiplying and multiplying. But what really happens? Can rabbits keep living forever and ever and keep multiplying if there's only a certain amount of food or water, or if disease starts spreading because they're overpopulated? So exponential growth is great, but it's usually not what really happens. What usually really happens is something more called logistic growth. So it kind of starts out growing exponentially, and then all of a sudden it's going to take this turning point, and it's going to start to flatten out. Where this guy right here is going to be your carrying capacity. So you can only have this amount. That's all that's sustainable for the given conditions. All right, so let's see how that pertains to this example. Animal populations are not capable of unrestricted growth because of limited habitats and food supplies. Under such conditions, the population follows a logistic growth model. So here's our model. C, D, and K are positive constants. Then it tells me for a certain fish population in a small pond, it gives me my D, K, and C. So let's fill those in. And then it tells me T is in years, and P of T would be the amount of fish. So let's look at part A. How many fish were originally put in the pond? So we're going to find P of 0. So times 0, that's the original amount. All of that's going to go to 1. Oops. Started to do that in my head. The 11, which is going to be 12. So I get out 100 fish. All right, see if you can keep solving for part B and find the population after 10, 20, and 30 years. Might be a good time to pause me and see if you can do that. Once you have it, you can come back and unpause and check and see if you got the right answer. If you didn't, make sure you ask me in class. Okay, and then part C, it says evaluate P of T for some large values of T. So just pick some really big values. You can look in your graph, you can put some in your calculator and see what you think is approaching as you go bigger and bigger and bigger. So what is T approaching, what is your fish population, P of T approaching as T approaches infinity? And I got out the carrying capacity of 1,200. See if you did too. We can support this graphically if you want to look at the graph of this equation by seeing this carrying capacity, what your horizontal asymptote is going to be, which is 1,200. Now don't forget your calculator is going to round, so if you're looking in your table, it's going to take 1,199.999999 and round to 1,200. So don't just assume that you get out 1,200. It's what it's approaching. You don't actually ever get the 1,200. One more question. Let's see if you guys can do this one. Fill it in. And then pause me and come back and see if you got it right. All right, so I've got Q of 5 to be 2.719, Q of 10 to be about 4.945, And as I keep going into some big numbers, I'm going to see that my carrying capacity, the most I could get here, is going to be 15. And this is in pounds. So as time increases with the minutes going, your carrying capacity is going to be 15 pounds. So it starts out, your graph starts out exponentially, and then it's going to start to flatten out more with logistic growth. And just for all of you guys who want a little extension, this little point where it goes from a happy face to a frowny face,